Good evening, everyone, and welcome to the John H. Carlson Lecture, The Ocean's Natural Way to Stop Climate Change with Dr. Jess Adkins. The New England Aquarium Lecture Series event is presented by the Lorenz Center, the Department of Earth, Atmospheric and Planetary Sciences at MIT. Tonight's event is made possible with generous support from the Lowell Institute, which allows the aquarium to offer these lectures free of charge to the public. My name is Dr. John Mandelman. I am the Chief Scientist and Vice President of the New England Aquarium's Anderson Cabot Center for Ocean Life. I am also our Interim Vice President for Animal Care. It's my pleasure to welcome you to the Simons Theater tonight here on Central Wharf, and it's also a pleasure to welcome our online audience tuning in remotely. The New England Aquarium is an ocean conservation organization that is working for vital and vibrant oceans for future generations to come. Tonight's speaker, Dr. Jess Adkins, shares our passion for the ocean and has dedicated his career to oceanography and the study of the history of the Earth's climate. Dr. Adkins is the Smits Family Professor of Geochemistry and Global Environmental Science at Caltech's Division of Geological and Planetary Sciences. And while he makes his home in California, he's no stranger to Massachusetts, having pursued his doctorate from MIT Woods Hole Oceanographic Institute Joint Program in Oceanography. And now, here to tell us a little bit more about Dr. Adkins, please join me in welcoming to the stage Dr. Daniel Rothman, Professor of Geophysics and co-director of the Lorenz Center at MIT's Earth, Atmospheric and Planetary Sciences Department. Dr. Rothman.
Thanks, John, and thanks to the Aquarium for hosting this 10th annual John Carlson Lecture. And we're especially grateful to John Carlson for making this lecture series possible. The Lorenz Center, in particular, very much values this opportunity to bring the excitement of basic science, basic climate science to the general public. The Lorenz Center is devoted to learning how climate works. One of the ways to do that is to study the role of the oceans in climate change. The oceans not only absorb heat and carbon dioxide from the atmosphere, but they provide a record of past climate change and sediments and other deposits. Tonight's speaker, Jess Adkins of Caltech, is one of the world's leading experts in the ongoing effort to determine how these natural historical archives inform our understanding of the mechanisms that drive natural climate change. This lecture is going to be a bit different, I expect. And in the course of his research, Jess has developed fundamental insights into the ways in which carbon dioxide is absorbed by the oceans. Earth scientists know that this aspect of the carbon cycle is intimately related to the stabilization of climate at long timescales. But might it also provide a solution to modern climate change? Jess is here tonight to tell us how this might work. As we've sort of heard from John, but I'll amplify the message here. At MIT, we're especially proud to count Jess among our alumni. He was in the MIT joint program with Woods Hole, as you've heard. And I'll add to that he did his PhD under the work of our colleague at MIT, Ed Boyle. Jess eventually migrated to Southern California, and he's been on the Caltech faculty for the last 22 years. We're delighted that we've been able to lure him back to give this lecture. Finally, we'd like to ask you that you should leave your questions to the end. And when it's time for questions, we'll be especially interested in any students, that is students before college in the audience, and we'll give priority to them, right? And then we'll take questions from everyone else, and we'll also be taking questions from our online audience, right? So without further ado, let's welcome Jess Adkins.
Thank you, Dan. Let's see. I hope that you guys can hear me. That actually sounds promising now that I'm up here. Yeah. Thank you, Dan. Thank you, John. And thank you, John. Right? There's a lot of Johns here to thank tonight. But mostly thanks to you guys for showing up here in person and online. And as Dan alluded to, I'm going to talk to you about something that is pretty new for me to be working on. It's not my sort of paleoclimate roots, but they'll show through a little bit in this talk as we go along. And so this talk is the ocean's natural solution to climate change. Another way we might think about it is how antacid might help save the ocean and help us store CO2 in the ocean as we go. I'm going to talk to you about how that's actually kind of an excellent, not even analog, but the way that the ocean goes about mediating CO2, and it might help us. I've had a lot of help along the way with a number of really fun colleagues. Will Burleson, who's listed up here first, is my dear friend and long-term collaborator at USC. Even though he is a Yankees fan and I'm a Mets fan, we still managed to get along. Adam, John, and Sitcha, Jacqueline and Holly are all terrific students who are either in the lab now or have been through the lab, and it's a lot of their work that you're going to see some of the pieces of here tonight. Okay. Finally, my own personal support for this group has come from a number of places, and there's a real Boston focus to this. I'd like to highlight the Grantham Foundation here, who have really been quite helpful in both providing some of the early funds to go after this applied work that I'm going to show you along the way, and to kind of whisper in my ear and nudge me along that maybe I should go do some of this applied work outside of academia. And I am indeed going on leave from Caltech starting in January to go pursue this as a company that we've just started to try to see if we can't try to remove CO2 at scale. And so I really appreciate all their aspects of advice, not just the financial support. Okay, so the first chunk of this talk is going to be why. Why would you want to do this, pull CO2 out of the atmosphere? And I'm going to do it through a few plots like this. This is the famous Keeling curve. It's the last 50, 60 years of CO2 measurements at Hawaii, started by Charles Keeling and now taken over by NOAA. And you can see all sorts of interesting things here. The first thing that you see is the sort of general rise from fossil fuel burning. You also see the seasonal cycle. You see the terrestrial biosphere breathing in and breathing out CO2 each year. Those are the little waves that ride on top of the mean. And it is this curve that might be one of the first motivations for, I wonder if that's supposed to happen, right? The CO2 going up like that. And so as a paleoclimate person, I immediately try to put this in some sort of historical context. So now I'm going to start noodling with this x-axis on you guys. I'm really going to mess around with it. Now we see 2000, the year 2000 over on the right, and this is about 10,000 years worth of measurements of CO2. Seems like a long time. And we can see that that Keeling curve is only the little piece over, all the way over on the right, just rising up. It's really hard to get your head around these sorts of timescales, so I thought I might help with a couple of milestones. Humans started planting things and really doing agriculture in bigger scales at the beginning of this era we call the Holocene, about starting 10,000 years ago. If we fast forward a while, CO2 hasn't done very much. I was in kind of a disease mode here as I put this slide together, for obvious reasons maybe. So one of the first plagues, this is Periclean Athens, the plague of Athens. We can move along to the Black Death at order 1,000. CO2 has risen by another, 5, 10 ppm, something like that. And of course, our own plague sits way over here on the right. These are long time scales for humans to think about in a relatively rapid change, but I think there's an even better way to think about this. Let's go even further out. So now this x-axis isn't 10,000 years, but 800,000 years, 80 times longer. This is the record of CO2 change and temperature change from the Antarctic ice core records. Up in the upper right-hand corner there is a picture of an ice core. I just think they're very beautiful, so I wanted to make sure that you sort of saw where these were coming from. You can see the dusty layers in the ice there. In some cases, and in this particular case, it's true, those are annual layers on the ice. It's one of the ways that we actually know how old it is. You just count, just like tree rings. And I hope you've had a chance to look at this long enough to see that CO2 and temperature, as measured here in the ice core, seem to be going up and down together. And it's one of the reasons it's really been motivated us from a past climate point of view to try to understand what's going on with CO2. Everything that I just showed you in the previous slide is in that arrow. We are conducting an experiment of unprecedented magnitude and scale. I don't think we need many climate models or you to see simulations or things to sort of understand That's a big hammer to hit a system that is kind of nonlinear in its behavior that we see beforehand. That is the right height that gets us up to about the CO2 concentration today. I couldn't make it thin enough, though, given the x-axis down here, and you'd still be able to see it, just to give you a sense of how quickly this change is coming about. This would be one of the first arguments for, maybe we should try to get some of that back. Okay, we know where it comes from. And it's actually a super interesting story, even for sort of a bland-looking plot like this. Over on the left-hand side is the year 1800, moving all the way up to close to today. And these are the emissions of CO2 in gigatons per year. Gigatons just a very large number. And divided up, the total is the big, thick blue line. This is the rate, right, that we're putting into the atmosphere on the upper part. And then below it are the different pieces of it. And so we can see early in the Industrial Revolution, solids are the main line. That is, starts as wood and then becomes coal. For the rest of this line, you can think of that line as use of coal. And for most of the CO2 rise up until the World Wars, it is coal, and it's not until the World Wars and then the rise of the American era. So we can see several things on here. We can see the Great Depression is a little blip in it. Here's the rise of the US economy post-war. That's the kind of thing that really gets this curve to go up. We can see the 1980s recession sitting on here. Those are all fueled, you can see, by what's called liquids here. That is oil, right? That is the liquid hydrocarbons that we know and love. And then you can see that there's another big acceleration up towards the end over there as the Chinese coal comes online. You can see the solids line kicks back up. There's all sorts of interesting inflections that you know from your own life in this history. The climate cares about the bottom plot. It doesn't actually care all that much about the top plot. The rate of input is something you hear everything about, and it's one of the goals you hear in the news all the time. How are we going to get off of fossil fuels and turn around our rate of emissions? The climate knows that we've already put in 400 of these gigatons, and it's going to keep coming at us. The bottom line is the sum, the running sum of the instantaneous rate that you see above. You might think about the top line as your credit card, right? And the bottom line is the inventory of savings that you're trying to build over time. And so we have to really worry, actually, not so much as about turning it around to get to zero rate of emissions, but what are we going to do about that historical? So there's another reason you might want to take CO2 out of the atmosphere. Okay, I'm going to switch units on you because it's a nicer looking figure. 10 on this plot is 40 on the next one, because this one is in carbon, the other one's in CO2. All right. These are the spaghetti plots that are a great way to sort of doze off and turn away, but I want to walk you through these a little bit so that you can see what's going on here with the spaghetti plots. Now we're looking at 1980 up to 2100. So these aren't historical records anymore. These are projections with a little bit of history of what's going on. And they meet there in the middle, that historical emissions line and the 2016 estimate. The y-axis is the same thing, this gigatons of CO2 emissions, the rate that we're putting up in the atmosphere. And these RCPs, these representative concentration pathways, that's a mouthful, right, are developed by modelers of the energy system to try and hit certain amounts of heating, just as a representative way of, if we did this in the economy, what would happen if we then ran a climate model and predicted what the temperatures would be? And so RPC 8.5 is 8.5 watts per meter squared of more radiative forcing that leads to 3 to 5 degrees of temperature change. That's the way to read this thing on the right. RCP 8.5 isn't meant to be like business as usual, or it was meant to be a comparison to if we didn't do very much. Everyone thinks we're going to do things. We've already started to do things, and so don't think of it as a business as usual. Though you might notice that our black estimates up to 2016 run right along the top line there, right? We haven't been doing such a great job of finding our ways onto any of these other lines. And the first point is this change in these RCPs, the way you get to lower and lower emissions and therefore lower overall temperature changes for these particular pathways by 2100, is by adding in more non-fossil fuel sources of energy into the energy models. So that's renewables, right? That's things like wind and solar. So here's an example of wind and solar on one day in California, right? I've got a California bias here, April 3rd of this year. The black line is the total demand, and the background lines are wind and solar. And so you can see that in the middle of the day, wind and solar do a nice job of meeting the demands, and on the wings, not so much, right? In the early evenings and in the beginning. And this is the problem. For some reason, this gets called the duck curve. Please don't ask me why. Literally, somebody thought when you subtracted these two things, it looked like a duck. And that is actually stuck. So you'll hear this sometimes referred to as a duck curve. It's a really interesting and important problem for people to work on, and they're working on it actively, of how are we going to get when the renewables are high but demand is low, how are we going to switch that to the time when renewables are low and demand is high? One interesting idea I kind of like is that in 2020, there were 277 million cars on the road in the US. And at that same time, US household used 222 billion kilowatt hours of electricity. If you just divide those two things into each other and do it per household, that is a battery that a household would need that's 80 kilowatt hours. That's what's in your typical electric car right now. If we instantaneously switched all the cars on the road from what they are now to electric, that would be enough installed battery power to solve this problem. You would charge your car during the day while you were at work and the sun was out or the wind was blowing, and then you drive it home, plug it into your house, and have it run backwards instead of the way that we do it now. That's the kind of thinking we need. That's the kind of engineering to go after to really try to understand how we could solve some of these problems associated with alternatives. I think these are sort of fun little calculations. Okay, but we're here to talk about taking CO2 out of the atmosphere, not going on to alternatives. They're not the same thing. They're often confused. They're even often confused in articles that you'll read in reputable newspapers, and we need both. We have to figure out how to get ourselves off of fossil fuels. But as you can see from this, the other thing that's in these RCP pathways is in a certain year, start taking 2 gigatons per year of CO2 out. Remember, our rate of input is about 40 on any given year these days, so it's not actually that big a fraction. And the only time that you actually get down to having a sort of safe climate, as defined by the Paris Accords, is RCP 2.6 down there all the way at the bottom. And we had to start removing in 2020, that already happened, 2 gigatons per year, and we have not done it. That's what we're confronting. It's not a chicken little statement. It's just it is a statement of this is what we need to pull forward and get working on. How are we going to get CO2 out of the atmosphere so we don't get these horrific looking warmings off to the right? Okay, so what are some approaches to this, to carbon sequestration? You hear a lot about planting more trees. I love planting trees. There are trees in the yard that I grew up on that are still there that I got on Arbor Day when I was a kid in elementary school in Westchester County in New York. I love planting trees. They're not a particularly good solution for sequestering carbon. I'm sorry to tell you that. But trees, every year, trees do great photosynthesis is wonderful, and there are lots of microbes and termites. And in the fall, like it's happening now, there's lots of respiration, and they eat up almost all of that primary production, and it comes right back at you. Soil restoration has got a shot. That's an interesting avenue to pursue, but I don't know that there's enough room in the soils that we've disturbed to go put it all back in. You know that that has to be true because all the carbon that we're putting in the atmosphere doesn't come from soils, it comes from rocks. And so trees are not a particularly good scalable problem, let alone the water requirements that come along with it. Another one that you hear is pump it underground. Absolutely, we should pump CO2 underground in any place that you think you can pull it off. There are already problems associated with this in thinking about leaks and thinking about induced earthquakes, right? This is what the planet does. And we have known this for a long time, right? This is really pretty straightforward geochemistry and oceanography. The planet will react, the Keeling curve, eventually, with calcium carbonate sediments at the bottom of the ocean. Little shells that are made in the surface that trickle down through the whole water column and land at the bottom of the ocean. And they'll make the neutral salts. It's an acid base. The acid in the CO2 will react with the base in the calcium carbonate to give you the neutral salts of calcium and bicarbonate ion in the ocean. The problem is, it takes a very long time on human timescales. It takes something like tens of thousands of years for this process. We know something about it because volcanoes have put CO2 out into the atmosphere in the past, and we've been able to try to understand what's happened to the CO2 in the atmosphere when volcanoes have gone off or extra inputs have happened. The nice thing is the reaction produces these harmless dissolved ions, and so if we were to try to mimic this one, we're already on an important piece of the really important safe ground, which is try to do no harm in this intervention that you're gonna do. Remember, the CO2 emissions is already an intervention in climate. We're just trying to undo it, but when you undo it, it's incredibly important to make sure you're taking care of the ocean as you do it. That's why it's nice to follow this process. Unfortunately, and this is what got us started on this as a research project, it's supremely embarrassing how well we don't understand the rate law for how quickly those shells dissolve. So the rate at which they dissolve is on the y-axis here. The x-axis is a number that we invent so you don't understand what we're talking about, so you can't come in and like break into our field because you're smarter than us. The scientists do this all the time. This is all the way over on the left is equilibrium. 0.05 is 5% undersaturated, down all the way over there to 30% undersaturated. That is to say, relative to equilibrium for this mineral of the shells, the calcium carbonate in the shells, that's the thermodynamic driving force. These rate laws, this rate is equal to some expression up there at the top that have two fitting parameters, K and N. N varies in the literature anywhere from 1 to 4.5, and K varied by 3 orders of magnitude when we were getting into this field a few years ago. It was just, this means we started because of ocean acidification. This is the acid that's going into the ocean is pushing us to the right, and the corals are feeling that, that driving, trying to dissolve faster, and we couldn't tell you, if you dropped the coral in the beaker and bubbled in CO2, how quickly would it dissolve. And so at Caltech, we love isotopes. We love trying to figure out a way that we can manipulate the system so it's easier to measure, and that's what we dreamed up as a way to do this. And so this is the blue background is a bag, a gas impermeable bag that we have in the lab, and we put purely labeled calcium carbonate, pure C13 solid, just like those shells, into this bag, and we just monitored over time how quickly the ratio of C13 to C12 changed in the water. As it turns out, we can measure that about 200 times more sensitively than what people had been doing to measure that on those plots beforehand. That was our kind of analytical breakthrough in the lab to get a hook into this. And so over time, as the ratio of C13 increases in the seawater, we can see the rate. And so the basic workflow of an experiment is you have a bunch of these labeled calcium carbonate grains. They go onto a shaker table in the lab. They're those gas impermeable bags. You wouldn't believe it, but those little valves that you see there, that was like 4 months of work figuring out how to make those valves work. And then the manufacturer changed them, and we had to do it all over again. We had to sample, then you take samples of the seawater out over time, and you run them on one of these awesome cavity ring down spectrometers in the lab. This is the one in Will's lab at USC. I love being in the lab. I love being an analytical chemist, and I can't help but show. I'm going to show you a few different bits of like fancy machines as we go along here. And so there's one of them. And then the basic data is really pretty straightforward for even folks like me to interpret. Moles dissolved, how much carbon came into solution on the y-axis, and then how quickly the clock went along, right? Over tens of hours. It's a sort of week-long experiment. The really steep lines that you see at the top, those are further away from equilibrium, and so they dissolved faster. And the shallow sloped lines that you see down at the bottom, those are ones that were closer to equilibrium and dissolved more slowly. And so the slope on this plot is what we're looking for, is the rate. And so that was really fun, and John Navio went whole hog in trying to look at the temperature dependence of this, and he sewed up the plots so well. This is now a log-log plot, right? So now it's log base 10 on the y-axis and the same driving force, but the left-hand side is 1% undersaturated, the middle is 10% undersaturated, and then all the way over to fully undersaturated. There were these kinks in the rate law. Those kinks are changes in the curvature, right, when you plot this in the way that I first did. And the fact that those kinks are there is why everybody who were making good measurements in the lab got such different answers for K and N. Is it mattered where they were making their measurement along that axis. And so they were doing great, they were doing a nice job of measuring the rate. It was just extrapolating it all the way along that was the problem. Getting 200 times more sensitive let us come into equilibrium and start to find all of these kinks. In fact, we then began to understand what the source of these kinks are. It's literally the nanometer scale, the like nanometer to angstrom scale, the atom by atom forces, energetics of trying to remove a little bit of calcium or a little bit of carbonate ion from the surface of a solid. So we're over on the left, you have close to equilibrium, and the only thing that you can dissolve when you don't have much free energy from solution are things that are already almost dissolved. They're little peninsulas sticking out all there, these step edges that retreat. But if you come further away from equilibrium, you give the system a little bit more chemical potential energy that way, you can start to pluck things out from defects in the surface, and then go all the way over to really high energies, and you can begin to pluck them out of the 2D flat surfaces, and the thing runs away and dissolves really quickly. The transition between those three states are those kinks. That was a really good day. That was a fun day in the lab. We then said, look, it's not enough to do it in a lab, we're oceanographers. Is this actually what's going on out in the ocean? Which is what's really fun about being an oceanographer, is going to sea. And so there's one of the things that we built on a particularly stormy day off the back deck of the Kila Moana in the North Pacific. That thing that's hanging on the wire is this. It's one of those bags, but in a little bottle that we can close while it's hanging on the wire out at sea. It's got a pump and some batteries. This is one of the things that's really fun about working together with Will, is inventing these little Rube Goldberg machines. And when we go and do that in the open ocean, we can see there's the 5-degree data in the lab. So it's again the same plot of rate on the Y and the driving force on the X, the red circles of the lab, and the blue circles of the North Pacific. That same kink showed up. That also was a good day. It's 4 times slower. That was a really interesting story to try to figure out why it's offset. But these kinks that we're finding in the lab, we also find out in the ocean. I told you, though, that the rubber hits the road for what the ocean actually naturally does is down in the sediments. And that's very hard to access and try to do these kinds of experiments. So over on the right of this plot, this is something that an illustrator who came out to sea with us, Molly Murphy, made for us, is trying to, almost at scale, show you what it's like. You couldn't draw the ship small enough for the size of the ocean to get down thousands and thousands of meters to the bottom of the ocean, and yet that's what we need to do. We need to go somehow put one of our bags, some sort of version of our instrument, down at the bottom of the ocean so we can go study whether those kinks appear for the dissolution rate at the spot that we actually think that it really matters. We brought all sorts of other instruments. That's what we see over here on the left. The multi-core that you see there is one that we're going to look at now. Here is a multi-core outfitted with another thing that we built a few years later in the labs that we thought we could inject into the sediments and be able to get our rates. So that bat wing looking thing down at the bottom, the black thing with the white holes, is a blade that's hanging off of a bunch of coils that are hooked up to syringes and springs. And that blade, with those holes that are filled with filter paper, that's what those white squares are connected by a little drilled in tube that goes up to the coils so that we can insert the blade into the sediments, trigger the springs to suck on the syringes and pull water out of the interstitial waters inside the sediments in the upper 10 or 20 centimeters in a total Rube Goldberg device. And so here we are on the back deck of the script ship, mounting it onto the multi-core. Here's a nice close-up of what it looks like. These multi-cores also are taking cores. That's what you see in the clear plastic tubes. And of course, you can also find other things to do with a multi-core at Christmas time. It became our version of a Christmas tree. Don't ask me what those guys are doing. And this is about day 37 at sea. So, okay, so here it is. We managed to mount a camera for some of the shallower ones. It only went down to 2,000 meters instead of 4,000 meters. Our camera would have imploded any further than that. And so here is the multi-core headed to the bottom. And as the bottom looms out, it hits and slowly injects it. I have to admit, I really like that. That's 2,000 meters below our feet on the ship as an autonomous robot, right, that we've dropped off the side. It's still attached to the ship from a wire so we can pull it back up. It's good. Let's watch it again. It does warm the cockles of my heart, this one. So just because it was 3 years in the making of getting this thing together, and the first time it worked was Station 1 on this cruise. That was our one shot to get it to go. The syringes then fire about half an hour later because we wanted to give it a chance to settle. It pulls water for about 10 hours, and then we pull it back out and bring it on back up to the ship. Of course, being at sea has all sorts of other fun things that go on. Like I said, it was the holiday time, and so we brought Mr. Snowy along with us. We see over here on the right a couple of our scientists taking a break. You can see the beautiful coastline of Costa Rica in the background. And then, of course, the captain had to play some golf. Notice his approved footwear that he's wearing here, too. Come on, Captain. You can do it. There you go. There you go. See? There you go. So you're at sea a long time, right, on these sorts of things. You're out in the middle of the Pacific Ocean. You're trying to walk up to get in as much sampling as you can. You have to find things to do. That golf ball was made out of seaweed, by the way. Will found those. It was such a treat when he pulled these things out. So, and the captain, of course, immediately came down and took the club out of everybody's hands. He's in charge. He can do whatever he wants. And started knocking all the balls on the ocean. It was a fun day. Okay, here's the thing. The data from that lander is over here on the left. I'm showing you the data I just showed you before on the right. Same thing, rate on the y-axis and driving force on the x-axis. The kinks are there in the sediment also. That is not just a good day. It happened just actually about a month ago that Holly and I plotted this up. It's this modes of dissolution are the way that the fundamental science is actually working, the way that the fundamental rate law is working. So how are we going to harness this to help us think about how to take CO2 out of the atmosphere? Well, we had this really awesome, another good day in the lab, or actually it was sort of like a month in the lab, that my student Adam discovered a catalyst for the reaction as well. He put carbonic anhydrase, an enzyme, into those bags, and it went 500 times faster, this dissolution rate. So that was kind of cool, because remember, it's super slow. This is what kicked us out of the basic science mode and into engineering mode. Once we realized that we were able to make the reaction the planet does naturally go faster with a natural enzyme, we thought, oh, wait, this is more than just understanding the basic science of the rate law. We have to think about whether you could scale this up. And that got us to work building reactors in the lab. Here's a fluidized bed reactor. It's actually 2 of them sucking water out of a tank that's there in the middle, bubbling CO2 in the presence of limestone and inside seawater. So just a schematic of what's going on there. There's seawater coming in at the bottom. There's gas, CO2 gas coming in at the bottom as well through a little bubbler. There's already little grains of, like those shells on the seafloor, little grains of the calcium carbonate. That's the antacid. Just like when you take a Tums, the extra acid in your stomach is getting absorbed by the reacting with the Tums. We're trying to do the same thing, but inside this chemical reactor, so that CO2-rich gas comes in the bottom and CO2 lean gas comes out at the top, and the little bit saltier water with the calcium and bicarbonate ions goes out to the right. Okay, so we got to work. We said, hey, Caltech, could we hook up to a real CO2 source, the power plant that Caltech has, the cogen plant there, 10 megawatt power plant. And we hooked up our reactor that you see there on the left, and then on the right, this is a time series, so it's about 25 hours a day of collecting data. And at hour at hour 5, we injected some of the catalyst in there. And indeed, the reaction went faster. We got more of our reactant out. That's what's on the y-axis. And that's great, except that's catalyst that's in the solution that's just flowing out of our reactor as it goes. We had to figure out a way, because it's really expensive and you don't want to just start dumping a whole bunch of enzyme back out into the ocean. We had to figure out a way to get it trapped and hold it in the reactor. And so we had to start learning a bunch of biochemistry, stuff that we're not naturally good at in the lab. There were 2 basic approaches. Encapsulate it in some sort of funky silica gel. Those were really fun to have around the lab because they're all kind of gushy and wobbly, and so they're fun to play with. Or covalently bond it to something. In the case, we picked silica glass beads, like little porous glass beads. This took about 2 years of work to figure out how to do this, mostly because we were kind of novices. Other people had done things like it, and we were just kind of following in their footsteps. And we were able to get it bound and keep the activity. And we got very excited. We said, great, let's take our glass beads. That one worked better than the silica gel. Again, we're going to go put it into a reactor, this time in the lab rather than hooked up to the power plant. And that's the thing over there on the right. And at 400 minutes there, in between 300 and 400 minutes, the reason there's a gap is because we took off the lid and we added our glass beads and nothing happened. And John Navio, who is the student at this point, got very frustrated, right, after the couple hundred minutes there, and he said, "Meh!" And he just injected the dissolved catalyst in to see if there was something going wrong, and the rate bumped way up. Uh-oh, right? The catalyst was active, we had tested it, but it doesn't make it go faster when we get it to be held in. Ugh. That was a bad day in the lab right there. We did some nice science to figure out why that required another really fancy instrument. This is an atomic force microscope. This work was going on in parallel, and they just happened to land on the same result. The atomic force microscope is over here on the left, or at least on my left above me. And you make pictures of a surface, 10 microns on each side. That's already pretty small. That sounds neat. But the cool part is that in height, in Z, it can measure nanometer or better heights. So you can measure those little steps that I was showing you pictures of. You can see the reaction, like spot by spot, dissolving away. And you can see that here on the right. You go from 0 minutes in the upper left to 10 minutes in the lower right. And where there's a little square that you see in yellow, it begins to grow. That's an etch pit growing larger over 10 minutes. And it's one of those steps. It's about a nanometer step up from one to the other. Really amazing little instrument. And we did the same thing, but with carbonic anhydrase in there. There was enough of it that it flocked together. So those little clouds that you see on the left are drawn on the right are the enzyme, are the catalyst. Where it touched the surface, we had a hard time making a measurement, but at 3 minutes later, some of it fell off, and there were a bunch of etch pits underneath. The catalyst is terrific if it's allowed to touch the surface. But when we bound it to the silica particles, now it couldn't actually go touch the surface, all the little calcium carbonate particles, and so it wasn't being catalytic. It was still active as an enzyme, it would still work. That's a really nice piece of science on the mechanism of what's going on, and is a total solar plexus shot if you want to remove CO2 in this natural way. Yeah, but fortunately, we had been thinking during this 2-year period, and this other part took another 6 months of figuring this part out. We'd been thinking about what are we going to do once this catalyst works? Because of course it's going to work, right? It's going to be great. And that started to point us toward, it was a big bummer when it didn't work. I think I've just said that. That got us thinking about the shipping industry. We were thinking, where are we going to, how is this, what's the application? So what that we're able to make this go faster? Is there some place out there that we could marry a source of CO2 with our reaction that we could go do this good work to go make saltier water in the ocean and remove CO2 out of the atmosphere? The shipping industry is a natural marriage for us. They're 3% of global emissions. It's a big number. They have about 3 to 5% CO2 concentration in the flue gas, so they're a point source. They make a lot of acid if you bubble it into seawater. They have a vast capacity to carry limestone. These ships are some of the largest objects we make as humans that are floating across the ocean. And seawater is, quote, free resource as you go. And then from a business point of view, they're already under regulatory pressure to do something about it. They would pay us if we could figure out how to help them decarbonize by running our reaction. Okay. So there are a lot of ships out in the ocean. Just a few back of the envelope calculations, because you might start wondering, is this really even possible? One shipping container, it's called a TEU, is this particular size. There are 10,000 or more of them on the largest Panamax size vessels. We need about 24 of them full of limestone every day to keep up with the emissions. This is just a statement of the size of the problem that we're up against, right? So that's a fair bit of limestone. That takes up about 4% of the total volume on the cargo ship. At 20 knots of ship speed, the ship is a big water pump. This is actually a really beautiful marriage of the things, because this is called the accelerated weathering of limestone, or AWL. It's in all the review papers about how to take CO2 out. And it's always dinged for having to pump a lot of water uphill. But if you're doing it on the ship is already a massive water pump for you. If you just make holes in the hull and have the water come through your reactor and then run off the back. Okay, and then our techno-economic analysis of this, that we think we come in at about $77 a ton for CO2 sequestered. I wish it was cheaper, but I'm glad it's not 700. We're actually sort of in the game of the economics of how this works at $77 a ton. So we get into the lab. We built a bunch of different versions of the chemical reactors. This is a packed column stirred tank. We can model it with what you see on the right. The contours that you see here is the percent efficiency of removing CO2. The goal for the shipping industry by 2050 is to be at 50% levels. And so in all of these, we're hitting those levels. This December, the rubber really hits the road. This lands at a parking lot in Los Angeles. This is a 16-foot tall version of those reactors connected up to a real diesel generator over on the right. And that is a artist rendition of Pierre Forin, a staff member that works in my lab. So we have something that looks like a human over on the side. We're going for it. we're going to try to see what does this look like if you scale up. We're going to try to technically de-risk two parts of it. One is if we try to bubble in the exhaust from the diesel generator, just like the thing that we would try to do on the ship, that's like sticking a banana in the tailpipe of your car, right? That's going to choke off the engine if you put a big pile of water on top of it, if we're going to try to bubble it in. We've built a bunch of blowers. That's some of the stuff you see in between. So to buy us about 9 feet of hydrologic head. That's why we have this big, tall reactor off to the left. We have to demonstrate that that actually works. We also have to demonstrate that the reaction going in the lab and the scaling that's going in the lab actually work as you come up to scale. This is the same height that we would put out on a ship. Of course, we would need many, many more of these strung together if we were to do all the CO2 coming out of a massive cargo ship rather than, say, this diesel generator. And so this was kind of COVID that did this to me, right? This was getting inside my own head, sitting in the back of my garage, right? Not being able to interact with anybody. It's a very privileged thing to be a Caltech professor as well as being an MIT professor. And I really see it as my job is try to figure out what's the most important thing that I could try to pull off. And this earworm of trying to take the CO2 out rather than thinking about how the rate works in the lab just kept getting into my head. And so we're going to try to go for it. I'm inspired, and this will be the last slide here, and I'll be happy to take some questions. I'm inspired that we've actually done stuff like this before. CO2 is global, right? And so it's an even harder problem. But here's an example, and I love this picture because it comes from Ed Boyle, my former advisor that mentioned. This is the lead concentration in corals off of Bermuda, going back to 1850 and coming up to 1990. That peak that starts to turn around there, that's the Clean Air Act. That was specifically designed to take lead out of gasoline, and it stopped appearing in the natural environment in Bermuda. Good environmental laws can work. They can actually clean up the environment. I think this is one of the best examples that we have. We're no longer polluting ourselves with lead thanks to the Clean Air Act, and the corals are recording it beautifully. This is work that Glenn Shen did with Ed long before I was in the lab. We've done the same thing with acid rain, and we did it based on a cap and trade program. We actually had economic incentives in place to try and help make sure that the good science was aligned so that the industry was forced to end up lowering its emissions. I really think we should have hope about this. I don't think we need to crawl into our sort of Chicken Little caves and say, oh my gosh, we've just created this huge problem, because that means that tomorrow you're going to go buy an SUV that burns a lot of gasoline, right? There are things out there that we're trying to pull off that I think we have to pull off, and we need your support, we need your criticism, we need your advice on how to try to do it. So that's a good moment for me maybe to take your questions. So thank you very much for listening. I'm happy to hear from you.
Thanks, Jess, for a lovely talk. So as I mentioned at the outset, in my introduction, that immediately after the talk, we'd like to prioritize the questions from any students in the audience, that is students who are high school, junior high school, or whatever, but not college yet. Don't be put off by that. No students? Okay, if you're there and you want to ask a question later, we'll take it gladly. We'll also be taking some questions from the online audience, but let's begin with someone in the room. There's one right there. We need to repeat the question.
Yeah, I'll repeat the question shortly. The question was, where are we going to get all the limestone? It's a great question. The surface of the Earth is blanketed in limestone. Limestone is not a limited resource, but of course, the ability to mine it, crush it, and transport it, right? We have to think hard about how much energy and how much CO2 emissions we're doing in that. That's included in that $77 a ton that I gave you. And then when we do and we need to do a better job of this, but the first shot that I've taken at it so far, we're about 10 to 1 on carbon. So for every 10 carbon atoms that we're going to remove, we'll have released 1 in the process in order to get, and most of that comes from the limestone, and some of it from the having to pump some of the water around. Yeah, great question, but limestone's not a limited resource.
Yes. Have you talked to any lawmakers yet?
So I have talked to regulators. So I've opened a conversation with the EPA because it's incredibly important to involve regulators early on in the process. We haven't done a single thing except worked at the lab yet, right? And the first thing we're going to go do is work in a parking lot. And so we're still months, maybe even a year away of actually putting this on a ship. And so now is the right time to be talking to the EPA. And so it's a great question, but I'm going to use it to launch on a thing that's even more important to us, right? But this thing sequesters carbon. It's not that hard, right? This is not some like magic technical thing. It was hard to figure out what the rate law was, but once you know that, you can go design the chemical reactor. And the EPA is going to be a great way to get the permission to do it, at least as a research project. That's not our biggest hurdle. Our biggest hurdle is the social and political license. It's you guys, whether you think it's okay to go do it in the ocean, right? Because, and I was here, right, a decade ago, not physically here, but mentally here. Was there another question? Okay. We have an excellent track record of trying to solve some environmental problem and making something else worse, right? And so an attitude of, we messed up the atmosphere, we don't get to mess up the ocean also, 100%, I get it. We're cooking ourselves. It's coming down to a decision of which one do we want, right? Do we want to get hotter or do we want to take some shots at taking CO2 out of the atmosphere? That has to be a public discussion, right? That can't just be me telling you, you must follow my lead on this. This has got to be the way that it goes. We need the social and political license to actually go carry out this stuff in the ocean. So please pay attention when I ask for public input, right, about what you think about this. We are the sorts of scientists you would turn to ask the question of, is this going to do any harm? I showed you from the chemical side, we're pretty sure it's not. We don't know from the ecological side. So that's research that still needs to be done. It's a really important question that you're asking, and it's beyond just the regulatory part. It's really a much more important societal one.
Right here. She's starting, you're next. You had a question in front, right?
I wondered what you think this does to the cost of shipping and who pays. I don't know.
You.
Well, I don't know the shipping industry well, but I think it's about 1% of that.
Yep, no, it's a great question. And it's exactly the kind of thing I'm not good at as a scientist going out and trying to be a CEO of a company, but I'm learning. And so I do actually have some answers for you. Let's see, the first place to start is they're under regulatory pressure to do something, right? And it's getting worse, right? I'm under some sort of like, let's just talk with each other before we go public about this kind of NDA sorts of things. With a Jones Act shipper, Jones Act says that if you're going to go from a U.S. port to a U.S. port, you have to be a U.S. flag carrier with a U.S. staffed crew. This group that we're talking to, January 1st, 2023, this coming January, they're going to turn their engines down 25% because of the carbon intensity index that's coming on. Different than that 50% reduction pressure that I was telling you about that comes out in 2050. They feel this pressure very, very acutely. And so how much is it going to cost them? It's really how much is it going to cost you when these get passed on, right, from the shippers. They feel the stress to try and do this already. And so just from like, do we have a market out there to kind of go explore it? It's absolutely on the table. The most interesting application of this isn't just decarbonizing the shipping industry. You asked about carbon credits. It is, what if we just made a ship that was a limestone reactor by itself? Don't have it carry televisions or your shoes or oil or grain. Have it carry a bunch of limestone and CO2 that it picks up in port, or direct air capture that it does while it's going out there, and go out and mow the lawn out at sea in a place where we feel like it's safe to go put these this salty water. And now it's really a negative emissions technology, and that enables a cap and trade system, and that is really where we can make a difference. If we can bring about the ability to really make economically a real trading of, if you emit, then I'm going to take it away. That's how we solve the sulfur problem in acid rain, right? That's a spot where we really could make a big difference.
Just behind you, yes.
If you did this at scale, what is the byproduct? Does the ocean end up saltier, or does it end up more acidic, or less acidic? Is there some impact?
Yeah, it's a great question.
Yeah, the question.
Yeah, and I should repeat the question, which I think I didn't do before, so I apologize. The question was, if we go to scale, come on, what's going to happen to the ocean, right? Is it going to get more acidic, less acidic? Is it going to be saltier? You were guessing at all the right things, right, of the things to worry about of what will happen. If we perfectly match 1 mole, like 1 CO2 with 1 calcium carbonate, that is all the acid titrated with all the base that makes a neutral salt. We don't change the pH of the ocean 1 iota. That's in our effluent that comes out. We make there to be more of that neutral salt. There's already a lot of bicarbonate and calcium in the ocean. It's going to, the ship is an amazing egg beater as it goes through the water. It's going to do a good job of initially mixing away what's there, allow then ocean circulation to take over. Eventually, the amount of salt that we're adding is going to be unmeasurable. That doesn't mean you shouldn't worry about it, though, for the time before it became that and mixed away. And so the one that I think is on the table that we really need to think about is there some microbe out there that loves bicarbonate that is currently getting suppressed because things are worrying more about CO2 aqueous and carbonate ion. But when we start doing our thing, we're going to be putting on a bunch of the neutral salt, and that's going to allow this microbe to grow. You can go do that experiment in the lab right now, and people are starting to do it, and then we're going to have to try to do it in a real mesocosm, sort of carry it out in the ocean. We're going to try to answer that question before we do it at scale. But from a chemistry point of view, we think we understand it pretty well. I think the real questions come to what's the ecological impact going to be.
Right there.
Just to come back to the thread my question is about, which has to do with, you showed that there was good engineering, you probably moved over, but there was engineers working out how to solve, how to find the information and answers you want, monitoring and metering. But is it really, well, how much does it matter whether we get people involved in STEM, in science, technology, engineering, and math, to fill your laboratory, to fill these ecosystems versus people trying to change lawmaking? So should we be encouraging STEM to get these solutions made, not only studied, but made, or should we be mostly looking for people to change lawmakers' will? Because you have shipping people, there are some guideposts already, you have shipping people willing to work with you on pilots. What do you think about the balance of what we need to tell young people and people early in their careers? Should they go into environmental science, or should they do engineering and chemistry?
Yeah. So I'm going to try to summarize that question, and if I do a terrible job at it, yell at me, but I'm going to try to boil it down. It was essentially, hey, what are we going to tell folks who are trying to figure out what to do with their careers or with their lives? Should they go into STEM and try to help solve the technical sides? Or should they go into, I don't want to say lobbyists, go into lawmaking side or go into the policy side and trying to think what's the best way to get society's wishes implemented so that we actually can end up at a place where we're not going to cook ourselves? Did I do a good job with the question? Great. Look, I struggled with this myself, right? First and foremost, do something you love. That is like the way to have it not feel like work. It's okay if it feels like work. I like going to work. And I went to graduate school thinking my goal was to go influence policy. I thought that's why I needed to go get the imprimatur of this big fancy MIT PhD, and then people would listen to me in Washington when I had something to say. I was a naive guy. And then I fell in love with the research. And it was just fun, like discovering stuff. It was also even fun when it didn't work, right? The solar plexus shots, because it sort of immediately the next day spurned you. And I realized that's what I loved. And I left these ideas of, yeah, I'm going to go to law school, or I'm going to go intern as a policy person, all unbelievably cool things to do. It just wasn't for me. So I picked the STEM side and really followed like these sort of basic science questions about why does climate change naturally and why are there glacial cycles. And it was really only stumbling from a basic science approach, stumbling into something that might have an engineering one, that got me to now thinking about like trying to start a company and things like that. At each step of the way, all I've done is something that looked like the most cool and interesting next thing to do. That's how you should make your decision. If you choose to go to STEM, awesome, come join us, right? It's gonna be great. If you choose to go to policy, fantastic, help us understand what society's wishes are. I'm trying to put one into the conversation that I think would really help. Did I answer? I hope I answered your question. I can't tell you which one to do because you're you.
So the oceans are sequestering carbon every day, but we read that the oceans are acidifying. Do we understand why they're acidifying and what that acidity is doing to its sequestration capability?
Yeah, that's a great question. We know that the ocean is acidifying today, and do we know what it's doing to its capability to sequester? Did I get that right for the two parts? So the first part is tell us about the mechanism, what's going on with that acidification, and then what does it mean for carbon sequestration? So the ocean is absolutely acidifying. It's very well measured and very well understood why. The ocean has 60 times more carbon in it than the atmosphere does in the natural cycles. And so up until we started burning fossil fuels, it was what the ocean did that determined what the atmospheric value was. It's only since we've gone directly to taking carbon out of rocks and burning it in engines and putting it into the atmosphere that we've knocked the system out of equilibrium. And it's actually the atmosphere that's now putting stuff back into the ocean. And that's where it can be really confusing when you read about this stuff, because we flipped it around only recently. And that acidity from the CO2 is what's lowering the pH of the surface ocean. That's actually the first step in the natural process of getting yourself to the base that's down at the bottom of the ocean. And because you have to start at the top is why it takes so long. That acidification has happened before on the Earth when more volcanoes go off. You acidify the surface ocean, eventually some of that water sinks into the interior, and finally that acidity is able to touch the base and the carbonate sediments down at the bottom. That's why we want to understand the reaction rate, because it's kind of slow. Then you actually need worms in a process called bioturbation, one of my favorite words, worms to come and stir up more sediment because you dissolve off the first layer of calcium carbonate. And so what we're seeing right now with ocean acidification is actually the first step of the process that takes tens of thousands of years to actually neutralize it. The corals don't have tens of thousands of years. We're doing it at a scale that's much larger than the natural system has ever done. And so that's why we're putting our ecosystems in peril at the surface ocean. But it is actually exactly what's gone on before. It's just we've ramped it up like you wouldn't believe. Is that the question you're asking?
So before I take the next question, I'd like to remind the virtual audience that they can put their questions in the chat, and we will take them. Is there another question? There's one all the way back there.
Do you believe that the saline water that's released might have an impact on the electrify and the conveyor?
Yeah, thanks. That's a really interesting question. So the question was, do I believe that the salt that we're going to put out, will it influence the halocline? I'm going to ask you about that in just a second, and then influence the global overturning circulation, or the global conveyor. Can I just ask you quickly which halocline you mean, or I want to make sure I answer your question specifically enough. Okay, great. Yeah, so the halocline is this like wake that's behind the ship that is a little bit saltier, I think is then what you meant by it. Yeah. Okay, so this is actually like the thing that I did in my day job. What are the natural changes in the overturning circulation associated with glacial cycles? How might they be driven by salt? How might they be driven by heat? There's no aspect of the salt that we're putting out that will have the ability to have any effect on that. I know that for a couple of reasons, because I know the rate at which it's coming out and the size that's happening, but we also can put it where we want on a ship. If we are just decarbonizing the shipping industry, you have to go along the shipping lanes where they're already shipping things. But if we move towards this one that enables the whole negative carbon economy, one of the beautiful parts about that is we can pick the places that it's going to be safest to go and release it. But I'm not worried about shutting down the overturning circulation. Salt-driven as it might be.
Question there.
So the timeline that
Yeah, the question was, given that the research we're doing is going to take years and then it's going to take decades for implementation, how optimistic or alarmed do I feel? Did I get that right? I'm scared, S-less. That's what I meant about COVID messing with my head. We are simultaneously designing the reactor, testing it at the lab bench, and building the pilot scale. You're not supposed to do that as a new company, right? You're supposed to actually do it in series, not in parallel. You're supposed to figure out your design, go test it out on the lab bench, work out all those kinks, then go. We don't have time. I'm really scared. I'm optimistic because I've got something that I think I can work on that's going to take a shot, and I know of lots of other people that have something that they can work on that are going to take shots. And I think that's great. I think that's sort of the like, you get scared and so you get empowered, but it can't take those decades that you just laid out. That's why we're in a hurry. Yeah, great question. You have one over here.
Is there one?
Just
Oh,
here in the
there.
fourth row.
I'm sorry, I didn't see.
Just like a follow-up on this, I am a little bit afraid that you show that it's readable, especially when you show that it's readable. It seems like authorization that people can keep on now emitting carbon. Now the coal industry in the US and everywhere say we don't have to worry. We can keep on using not even oil, we can keep on using charcoal, coal and everywhere. And it would be a race from whatever that implementation versus the other one. And the other one, I hate to say, that is what people know how to do. People know how to get coal and burn it and all of that.
Yeah.
What do you think? Thank you.
Yeah, of course. No, it's a good question. Sometimes, and I don't mean to pigeonhole it, but sometimes this question gets called the moral hazard question. That to just so the folks online know what we're talking about. The question says, hey, look, if you do this thing that enables us to keep burning at least in the ships, keep burning the bunker C that's in the ships, isn't that just to give a free pass to an industry that we need to shut down? And how do I feel about that? Look, I'm going to say something that half of you might not like and half of you might like, just given the demographic. I mean, we know how this country has gone. Fossil fuels are a demonstrable good for humanity. It's just impossible to get around that. We cannot have the lifestyle that we have now. We can't have unbelievably beautiful rooms and incredibly intimidating screens like we have up here. All of it is built by fossil fuels and has been since the Industrial Revolution. We haven't paid for the garbage. That's the problem. We haven't actually dealt with the beautiful thing. They're so energy dense. When, like, I live in Los Angeles, so it's all about the freeways, right? You're sitting there on this very short ramp in your car, and there's big 18-wheelers barreling down on you, and you think you have this little room, and you go and stomp on the accelerator. What you do, you're breaking carbon-carbon bonds made in the Miocene, right? Made millions of years ago, distilled down to be able to fit in your gas tank to give you the energy. You break those bonds to give you the energy to jump forward. Fossil fuels are amazing that way. We're just polluting the commons. It's like, it's a good analogy would be the garbage of medieval cities, right? You used to be able to just throw stuff out the window and have it accumulate in the streets, and finally everybody said, it really stinks to live in the city. I'm gonna move, or we're gonna invent garbage men and hire them and go pay our garbage tax so that we can have it taken away. We have to do that. Whether you like the companies and their behavior that have made huge, obscene profits off of being able to burn those fossil fuels, your life is better because they've existed. And now we need to figure out what to do about the garbage. At the same time, we absolutely have to get off of them, right? We have to find a way to get on to the actual renewable sources of energy that I was talking about in the first part of the talk. There's no aspect of carbon sequestration that I know about that actually is going to get us to the full 40 gigatons, and I don't want it to have to. We have to reduce our emissions by switching our sources of energy. These have to happen in parallel at this point. We were supposed to start in 2020, taking 2 gigatons a year out. in order to get, along with all the alternative energies that we had there. And so I think the moral hazard question just decides that you're okay with cooking ourselves, right? Like this is a problem of global societal scale that we have to take on in a clear-eyed way. Is that the question you're asking? Yeah.
I wonder whether, especially when you pilot, that on $77 economy, but then the other country don't want to pay for any of that.
Absolutely. Like, why did we get to be the ones that had our economy grow off of fossil fuels, and now we're going to tell everybody else not to do it? Unbelievably good point. It really resonates with me. I agree that that is something that is a geopolitical issue that has to be put onto the table. But if you don't have the technical solutions there to enable the negative carbon emissions at the table, you're negotiating with one hand behind your back. But of course, we need to think about, why do we get the free pass? It's the same thing with old growth in the Amazon, right? We got to cut down all our forests a couple of times, and now we're telling the Brazilians not to cut down theirs. That doesn't seem fair.
So we have some questions from the chat. And so one is, are there microorganisms at the sea surface that use carbonic anhydrase to form carbonate shells, and can we increase their activity?
It's a really great question. I think everybody got to hear it, and the short answer is absolutely yes, and not just microorganisms. Corals do it too. It's one of the things that we do in my lab, is study the biomineralization of how corals make their skeletons, and carbonic anhydrase plays an incredibly important role in it. Here is a great cocktail party factoid though. If we were to scale that up, if we were to precipitate more calcium carbonate by having corals grow, CO2 will go up in the atmosphere, not down. Very good for restoring coral reefs, like something that I think we actually have to do, but it is the wrong sign. And this is because the chemistry, right? And you have to remember, I had Mrs. Zook in high school. She was a wonderful chemistry teacher. Thank God, because she made chemistry fun, and I'm still doing it today. When you precipitate the calcium carbonate solid, that calcium and carbonate ion brings 1 unit of carbon that was in solution into the solid. Good thing, right? That's now not something that can go up into the atmosphere. It also brings 2 units of base that were in the water into the solid, making the water more acidic, which pushes the equilibrium over towards CO2. And you actually release more CO2 out of the ocean than you get from taking up the carbon in the skeleton of the shell. Growing more corals would be the worst thing we could do for global warming. It's an important thing for trying to figure out how to combat ecosystem degradation associated with ocean acidification, but it's a terrible solution to global warming. Because you can't, the way I like to say it, everybody likes to follow the carbon atoms, you have to follow the protons too. You have to think about the acid-base chemistry at the same time that you just think about the mass balance of the carbon. Okay, I'm sorry, it's chemistry. I love it, and I know not everybody else does.
So the next chat question is, what will happen to the fish in the ocean over time if you increase the salt?
So I'm no fish ecologist, and so you should really ask a fish ecologist the question, and I don't mean that in a trite way. I really want to separate myself, who's about to go and try and promote, right, try to get this technology to work and see if we, from someone who's going to check if it's working. That shouldn't be me that checks it at the same time. I know that the salinity increases that we're talking about aren't going to affect fish at all, though, from my understanding of fish. But you really shouldn't listen to me. We should have other people checking on Calcaria, our company that just incorporated 2 weeks ago.
Can't avoid this one. What's the name of your company? Can I buy stock in it?
Calcaria, and no. But there's a little bit better answer to that. Look, the most likely outcome is that it doesn't work. I understand that about a new business. I just don't see how it doesn't work just yet. We're going to go try to figure out the ways that it doesn't work as we try to make it work. But along the way, the really good way if you want to make money off of Calcaria is go buy a rock crushing company. because we're going to have to crush a lot of rock. It's a little bit like the wine industry. Like a great way to make a small fortune is take a large fortune and start a winery. I like wine. But the guys who make the money are the bottlers and the farmer, the servicers to the farmers, right? If you're a service industry to us, you're going to do great. It's much more risky to be us. So we have raised money from investors, the Grantham Foundation being one of them, and so we're not open for investment right now. But thank you for the vote of confidence.
So on that note, I think it's a good time to stop. So let's thank Jess again.
Thank you. Thank you very much.
Sneak in behind you, gentlemen, to make a couple of closing remarks before we adjourn. Thank you, Drs. Rothman and Adkins, and Dr. Adkins, for your fascinating talk tonight about your research, your new venture, and all the context and some fascinating answers to some great questions. Really a pleasure. As noted earlier, tonight's event was made possible with the generous support from the Lowell Institute. They've been supporting our lecture series, allowing us to show these lectures free to the public for years, and we are grateful for their continuing support. If you enjoyed the program and want to help support the Aquarium's ocean education and conservation work, please consider a contribution to the Aquarium's Mission Forward Fund at neaq.org. If you were with us in person this evening, and thank you to all the folks that attended virtually. If you're with us in person, we have about 15 minutes left to enjoy some coffee and tea in the lobby, so please feel free to proceed there. And thank you again to those that joined us remotely. We look forward to our continuing lecture series next Friday, October 28th, with acclaimed photographer and editor Whitney C. Johnson, Director of Visuals and Immersive Experiences at National Geographic. So that should be a great one. Thank you for coming out tonight. Safe travels home. Great to see you all. I'm in New York. Born and raised in the city.
I'm from Westchester. Yeah. I was Mets, Rangers, Knicks.
Some Knicks.